We're going to start off this video with a reminder of expanded and exponential form. So as a reminder, exponents are just repeated multiplication. If you have 3 to the 4th power, that's 3 times itself, a total of 4 times. And if I'm multiplying that by 3 squared, that's multiplying it by another 2 bases of 3. So in total, I have 3 times itself 6 times, which in exponential form would be 3 to the 6th power. Next, we have t cubed, so t times itself a total of 3 times, being multiplied by t squared, which is t times itself 2 more times. Because this is all the same base, I can write it in exponential form. T is being multiplied by itself a total of 5 times, so exponential form would be t to the 5th power. What do you notice about the bases? Well, the bases between the product and exponential form, they never change. They stay the same. So I'm just going to write same. What do you notice about the exponents in the first column compared to the exponents in the last column? Well, originally I had 4 and 2 and it became 6. Then I had 3 and 2 and it became 5. So what's happening here is when we're multiplying by the same base, we ended up adding the exponents. How did you find the exponential form? Well, we just counted initially, but now we know we can just add the exponents. So I'm just going to say that's the answer for both of these. We got some vocab to go over. When multiplying numbers with exponents, if the bases are the same, you add the exponents. So we're going to see that in these examples here. I'll do the examples. You're responsible for that on your own. When I take a look, if we're just writing in exponential form, I see that I have the common base of 6 and I'm multiplying. So when you multiply by the same base, you can add the exponents. The reason why you want to do this is giving you a simplified exponential form. So if I add 7 and 4, that gives me 6 to the 11th power. 6 to the 11th power, you can imagine, is going to be a very big number because it's 6 times itself 11 times. So just to show you what that would look like, 6 to the power of 11, hit enter. That gives you, I'm going to write it down as well on my paper, but it gives you a fairly large number as we expected. There you go. So we have 362,797,056. In example 2, we are multiplying by the same base of -7. Now keep in mind, when you're multiplying and condensing it, the base does not change. So it's going to stay -7. I must put that in parentheses to show that negative is a part of what's being raised to the power. And then I'm going to do -5 plus 2. So -5 plus 2 is a -3. Now, you can never leave your final answer with a negative exponent. That's not considered to be simplified or proper. Anytime you have a negative, you're supposed to use that negative exponent property, which says that it causes a movement. That movement makes the exponent become positive. So currently that -7 is in the numerator position. It's going to move down to the denominator. That act of moving it to the denominator will make the exponent positive, so now it's to the power of 3. And we're going to have that placeholder of 1 in the numerator, so it's a fraction now. So I have 1 over, I have a negative base to an odd exponent, so I know I'm going to have a negative answer. I can plug it into my calculator, -7 to the power of 3, hit enter. You see you get -343. So that's my final answer right there. One more, we have multiple different bases. As long as they have the same base and you're multiplying, you can add them together. So I'm just going to start off with the base of 3. I have 3 cubed times 3 to the 4th power. So that's 3 to the 3 plus 4, which is 7. Now I have a to the 4th and then -2. So I add 4 and -2 together. That becomes a +2. Because when you add a negative, it becomes like subtraction. Now I have b to the I have, let's see, a power of 3 and negative 1. So if I have 3 plus negative 1, that becomes 3 minus 1, or 2. Now this is not the most simplified answer. Whenever you have a number to a power, you can evaluate that. So in my calculator, I could plug in 3 to the 7th power, giving me 2,187. So this equals 2,187. That a squared, I cannot simplify any further, nor the b squared, because those are variables raised to a power. So what I want you doing is anytime you see a constant to a power, you should be evaluating that. You should be simplifying it further. I'm going to skip the on your own and jump straight to the next bit of notes. It says write the quotient of powers in expanded form, then rewrite using one base. So in expanded form, in the numerator here, I have 8 5s being multiplied together. So 1, 2, 3, 4, 5, 6, 7, 8. In the denominator, I have 5 cubes. So that's 5 times itself 3 times. What happens is, remember if you have something divided by itself, it cancels to 1. So this cancels to 1, this cancels to 1, this cancels to 1. I'm left with 1, 2, 3, 4, 5 5s being multiplied together. So in exponential form, that's 5 to the 5th power. For this one, if I have 6 4s in the numerator over 6 4s in the denominator, and I cancel out something over itself. Remember, these don't cancel to 0. We don't have nothing left. Something divided by itself is equivalent to 1. So they all cancel to 1 here, making this our answer. If you think about it, we had 4 to the, there were 0 4s left. Anything to the 0 power is 1. So that's just another way of showing you, hey, the answer is 1 here. Let's do another one. We have 3 x's in the numerator and 8, 4, 5, 6, 7, 8 x's in the denominator. 3 pairs cancel out to 1. Now this time I have 5 x's left, but it's in the denominator's position. So when I write x to the 5th power, I need to make sure I put it in the denominator position. Everything in the numerator canceled to 1, so we have that placeholder of 1 there. So let's talk about what's happening. What do you notice about the bases? From this form to this form, the bases, they never change. They always stay the same. It's the same idea with when we were multiplying. What about the exponents? So here we had 8 over 3 and it became 5. Here we had 6 over 6 and it became 0. Here we had 3 over 8 and we had a fraction, which technically, just so you know, is equivalent to x to the negative 5. So how do we get from 8 and 3 to 5, 6 and 6 to 0, 3 and 8 to negative 5? Well, what you're doing is you are subtracting the exponents. So that's how you're going to find exponential form. That's the answer to both of these short answer problems. So we're going to see that in practice on the next page. It says when dividing numbers with exponents, if the if the exponents are the same, bases are the same, then I think I mixed up my words. If the bases are the same, then subtract the exponents. There we go. That makes more sense. So if the bases are the same, you subtract the exponents. We're going to see that in example. Let's start with 4. We have 3 to the 8th power over 3 to the 5th power. Since the bases are the same, they both have a base of 3, that base does not change. It remains the same. And then I have 8 minus 5. When you're subtracting, it's important that you do the exponent in the numerator minus the exponent in the denominator. So it's 8 minus 5. When you subtract, that gives you 3 cubed then, which you could plug into your calculator and see you get 27. There's a lot more going on in example 5, so you can only combine things with the same bases. Taking a look at the constants first, I'm going to simplify those. 6 over 4 does simplify. Both of those things are divisible by 2, so that becomes 3 over 2. Now I'm going to take a look at the x's. I have x cubed over x squared. So remember, it's subtraction. So it's x to the 3 minus 2, which is x to the first power. So I subtracted 3 minus 2. Now I'm taking a look at the y values. Y is understood to be to the first power, so it's y to the first power minus y to the fifth power, so 1 minus 5. That gives me negative 4. So if I write y to the negative 4 here, that's a bit of an issue, isn't it? Because 1 minus 5 is a negative number, you can't leave a negative exponent in your final answer, so you are supposed to move that down to the denominator. There's another way that you can think about this. The higher exponent is where your base is going to end up. So x was bigger in the numerator. See how in the final answer x is in the numerator? The exponent in the denominator was bigger, and it ended up being in the denominator. Let's do it again. Example 6. So starting off with the x's, because those are the same base, I can combine those. 8 minus 9 is negative 1. So if I have x to the negative 1 here, it would move down, and I have x to the positive 1 here. You can write the 1, you can leave it off. It's kind of personal preference. Technically, it's most simplest form if you leave it off. Now the y's. I have y to the fourth power over y to the first power. So 4 minus 1 is 3. That's not a negative exponent, so it is going to stay up in that numerator. And then I do have a z. There's no other z in the problem, so it has to stay. It was already a positive exponent, so you have no business moving that around. So I have 4 cubed over z, or x times z. You're responsible for the on your own. We're going to jump to power to a power. When a power is raised to a power, you multiply the exponents and keep the same base. So power to a power, if you ever see something like this, you're just supposed to be multiplying them together. This is a to the 2 times 4, or a to the 8th power. That doesn't simplify because it's a variable to a power, so we're good to move on. I'll do another one with you. Why don't we take a look at this one? We have a base of negative 2, so that does not change. Your base does not change. But I have a power raised to a power, so I'm supposed to multiply these two exponents together. 3 times 2 is 6, so I have negative 2 to the 6th power. This you can simplify, so what you could do is go ahead and plug in. Now, keep in mind, this is a negative base to an even, so I am going to have a positive solution, but if you wanted to plug it into your calculator, that's negative 2 to the power of 6. You see you get 64. All right, I'll leave that on your own for you, and we're going to jump to this last one here. When a product is raised to a power, distribute the power to each exponent. So if you have multiple things raised to a power, not just one thing raised to a power, it's still power to a power property. You just have to give the exponent to each base. So this is understood to be to the first power. This is understood to be to the first power. So I have a to the 1 times 2, which is 2, times b to the 1 times 2, which is 2. And that doesn't simplify any further, so we're done. Now this one has a lot more. A lot of people forget a constant is a different base than the x. So I'm distributing that power of 2 to each of the bases, starting off with negative 2. That's understood to be to the first power since there was nothing written there. So 1 times 2 is 2. Now I have x to the 3 times 2, which is 6. Y to the 2 times 2, which is 4. Z to the 8 times 2, which is 16. Now I can simplify further. I'm able to evaluate negative 2 squared. Negative 2 squared is a positive 4. Everything else remains unchanged. So that's my final answer there. And then example 10. This is the last one I'll do with you. Distribute to each base. So keep in mind, the constant is different than the x value, which is different than the y value. You're distributing, so multiplying each exponent by 3. And I do have that times x to the 5th power, which is the same base. So this is recognizing when you're multiplying by the same base, you add your exponents, 6 plus 5, and you can simplify that 4 cubed, which is 64. And that would be your final answer.